units first. Kashmi, whenever you look at any quantity in physics,
Mm-hmm.
you always understand a quantity through its definition, its formula, and its unit.
Yeah.
Can you give me an example of any quantity with its definition and unit? You can choose any quantity for this.
So, for example, voltage.
Okay, let's take voltage. What would you define voltage as?
Voltage is the push required to is the force required to push a charge around the circuit, or
It
basically
is
around the component of a circuit.
okay, fine. It is
It's
a push that's required to move an electron from one point to another.
yeah.
Okay.
The symbol is V and it's measured in volts.
So can you define it as the work done per unit charge?
Yeah, right.
So as defined, what is its formula? V equals
So U by Q. Sorry, W by Q.
both work. U by Q is also is fine. W by Q is also fine. Okay. And what is its unit?
Volts.
Its unit is volt. And when you say unit, you mean the SI unit?
The SI unit, yes. I can't hear you.
You can't hear me.
Now I
How
can.
about now?
Yes, I can.
Okay, I think there was a problem with my internet for a minute. Okay, tell me. How do you break down volt?
How do you break down volt?
Correct. So you said volt is a SI unit, right?
Yeah.
But it's not the most fundamental unit. I'll come to fundamental and derived in a moment. But
Okay.
without going there, volt you said is not the most fundamental unit, or I'm saying. So if volt is not a fundamental unit, how do you break it down into more fundamental units?
I don't have any idea.
I'll give you a clue. It's in the formula that you just stated.
Okay.
The unit follows the formula, right? So the formula is V equals W over Q. You
Yeah.
said V is the quantity which is voltage, also known as potential.
Is it joules per coulomb?
Exactly. So it has a unit volt, which means work done and charge ka units will be joule and coulomb. Correct. Can you break down any one of these also into further smaller units? I think coulomb you can't. Am I right?
Yes.
Yes. Or can you?
I can break down coulomb because
You can.
current is coulomb per, like, charge per unit time.
Correct. Which means coulomb can be rewritten as?
Current into time. So I into T.
Correct. But that is the formula, or that is a symbol for the quantity. I want the unit. So ampere into second.
Ampere into seconds, right?
Correct. Can you also break down joule exactly like how you did coulomb?
Energy is power into time, so volts into seconds.
What do you say? Energy is power into time. So watt into second. Watt
What?
into second is correct. But I think you complicate things further when you use watt.
Okay,
Can you
so
break down into any other simpler quantities or fundamental? Let me use the word fundamental.
energy is I square R into T.
I square R into T. Again, current and resistance are not fundamental, right? There are many ways you can use. So you said energy or work done.
Yeah.
There are many formulas. You said one is power into time.
Okay,
Does not simplify. Power is I square R, V square by R, VI into T. All three
force
do
into
not simplify.
work done is force into
Force into displacement works.
Okay.
Force can again be simplified.
Yes.
Yeah, into
Force will be simplified into mass into acceleration. So which is
exactly.
kg.
So now write the units for these corresponding quantities that you mentioned here. M stands for mass, whose unit is
Kg.
correct. A is acceleration, whose unit is
Meter per second square.
correct. S is displacement, whose unit is
Meter.
oh. So kg meters per second square into meter. So combining all these, what do you get the unit of voltage to be in terms of fundamental units? kg
kg kg second meter square
meter square per ampere into
second.
second cube, I think, no? Because second power minus 1 second becomes second cube, correct? Yeah. So this is voltage broken down, or the unit volt broken down into fundamental units. So let me use this as a prerequisite to go into fundamental and derived quantities and then fundamental and derived units. Any doubt in this?
No.
How you can break down?
Understood.
Okay, great. So let me break down quantities as we speak. So whenever you learn about quantities, there are mainly two types of quantities that you always think about. One is a fundamental quantity. The other is a derived quantity.
Okay.
For context, here I've taken the example of speed. Speed is a fundamental or a derived quantity?
A derived quantity.
Correct. What gave away?
Sorry?
What gave away the clue that it's a derived quantity?
Because speed is defined as the distance covered per unit time, and we get it from the formula distance upon time. So that
Correct. The
it's
clue right here, meter per
measured
second.
by a formula.
Exactly. So there are 7 fundamental units. Can you name one by one? I'll start. I'll take length. Length is a fundamental quantity. What else?
And time,
Correct. Time.
mass.
Okay.
Just a second.
This is from chemistry. Amount of a substance.
Yeah.
Luminosity.
Okay.
What else? Length, mass, time, amount, luminosity. Angle measure. That's also one other quantity, although we don't usually write it. And you never use it, or mostly in math. So I don't have to write that. What else?
I don't know.
Length, mass, time. Okay, let's try the units. I think you'll get a clue as to what you missed. I'll give you, we used it just a minute ago. I'll give you the clue. Let's try the unit. SI unit for length is what?
Meter.
Meter, correct. Denoted by M. Time is second.
Yes.
We used it, in fact. Mass is?
Will current be a fundamental?
Exactly. Correct.
Okay.
Current. We just used it now.
Yes.
Yeah. You split Coulomb into current and second for this exact reason.
Okay.
Coulomb was not the SI unit. Or its quantity charge was not a fundamental quantity.
Yes.
Amount of a substance is mole, MOL, symbol. Luminosity, you don't have to worry. It's lumen, candela, all of the units. Current is an ampere. Okay.
Yes.
So if you remember, just a while ago for voltage, you used all this. You used kg, you used meter, you used second, and you used ampere.
So what
You found a way.
seventh one?
Seventh one is angle measure.
Okay.
Radian. We don't use it usually. So I usually refrain, especially in physics. You don't use it at least for your grade. So I don't usually bother writing it down.
Okay.
Any other quantity you can think of, whether it is right here, the example I have mentioned, which is speed, or the example you gave, which is voltage. Another example you gave was
weight.
Exactly. Weight, force. Weight is a type of force, by the way, again.
Power.
I can think of charge, correct, power. Anything you can think of is a derived quantity. And its units, specifically the units like volt, Newton, Pascal, the new ones you give, all of them are derived units. the derived quantities and the derived units can always be broken down into their respective fundamental quantities and fundamental units.
Yes.
To refresh, you said voltage is work done per unit charge, which is force into displacement by ampere into second, which is mass into acceleration into displacement by ampere. So I think I'm making a mistake here. I'm writing the units. I need to write the quantities. Current into time here. Current into time. Or you can further write it as mass. Acceleration is displacement by square of time into displacement divided by current into time. This is how you break down any derived quantity into fundamental quantities. Make sense?
Yes.
And once you break it down, you can write the corresponding units. So this was m s square by I into t cube when simplified. So the units correspondingly became kg meter square per ampere into second cube. So this became the fundamental quantity denotation and the fundamental unit denotation for voltage. By the way, voltage has its unit volt. The symbol for voltage is V. Its unit is also V, but let that not confuse you. It's one of the few quantities which has the same symbol for the unit and the quantity as well. Okay? Yeah. So this is your breakdown of fundamental quantities, derived quantities, followed by fundamental units and derived units. So whenever you take up a numerical question, I always suggest write data in fundamental or derived units, but in SI units always. For example, if speed is given in kilometers per hour, please make sure to convert always into the SI unit, which is meter per second, which is a SI unit of speed. The same also applies for resistance, for example. If resistance is given in kilo ohms, make sure to convert the prefix kilo into just ohms. Okay?
Okay.
Okay, fine. Any doubt in this? What are fundamental quantities, derived quantities, fundamental units, derived units?
No.
No. Okay. So can you tell me, so here in this statement, I've told that the equation speed equals 10 meter per 2 second, which is 5 meter per second is correct. But this equation, 10 by 2, 5 meter per second, this is incorrect.
Okay.
So can you see why I've explained this as incorrect?
Because the units aren't mentioned in the second step.
Exactly. The units aren't mentioned. So although, yes, while numerically solving, we don't represent units in every step of simplification, you do need to include them. The advantage of doing this is, one, you make sure the units are always in SI. Two, you don't have to look for the units after you're done solving a problem. You already know how it is, correct?
Okay.
For example, if you are lost for a moment, you don't know whether the units for speed are meter by second, meter into second, meters divided by second square. You just have to look at the simplification steps. Meter and second here are divided, which makes the unit meter per second.
Okay.
So it's just ease of knowing the unit. That's all you get by including the units in every step of calculation. Okay.
Yeah.
So you've seen these, right? What are these? You see these accompanying the units.
I did a wrong conversion in my examination, like the term examination. We were discussing the paper in class
I
today.
did. I do remember. Yeah. So what are these? Giga, mega, kilo, deci, centi, milli, micro, nano.
So basically the prefix is added to the SI unit, which
Correct.
give them, like, raise them by a power of 10 and change the value.
Correct. It's 10 raised to power. Yes, so all this does, these are scientific prefixes, and all they do is They help in ease of denotation of a value. That's it, for a particular quantity. That's all they do. They help in ease of denotation. For example, instead of telling you that the resistance of a particular resistor is 3300 ohms, 0.00 ohm, I can just tell the value of resistance is 3.3 into 10 to the power of 3 ohm, scientific notation. Or if I replace this 10 power by a prefix, like you said, so 10 power 3 is the prefix kilo, denoted by small k. I can rewrite this answer as just 3.3 kilo ohm. That's it.
Okay.
Scientific prefixes help me with ease of denotation of the value of a quantity. That's it, with the right unit. If you notice, one of the most common units that you use is also a prefix. For example, centimeter actually abbreviates as centi and meter, which basically means a centi is 1/100th. So that means whenever I say centimeter, or when I say the length of a meter scale is 30 centimeter, I'm saying it's 30 times 1/100th of a meter. Or it is 10 to the power of -2 meters. That is why when you convert centimeters to meter, you divide by 100. This is the whole premise behind that. Got it?
Yeah.
You might have seen these in other quantities as well, like kilogram. We
Yeah.
just used it, right? We just said mass as a unit kilogram. A kilogram is just 1 into kilo is 10 power 3 gram, or a kilogram is 1,000 grams. Some of the common prefixes you use are giga, which is 10 power 9, mega, which is 10 power 6, kilo, which is 10 power 3, deci is 10 power -1. There is one more here which isn't mentioned, that is deca, which is 10 power +1. Please remember that.
Does even
Deca is 10. Yeah, I'm sorry.
hecto?
Yes, it is. There is a prefix named by that, but you don't use it. The most common ones you use for your curriculum are deca, deci, centi, milli, which is the opposite of kilo, micro, which is the opposite of mega, nano, which is the opposite of giga.
Yeah.
These are the most common. There are more. There is femto, which is 10 power -15. There are more prefixes. In fact, there's a name for all prefixes from 10 power +1 to +15 and -1 to -15. But these are the most common ones that you use. These are the ones we need to be aware of. So the whole point of using scientific prefixes is ease of denoting the value associated with a particular quantity, especially if it's either a very high value or a very small value.
Okay.
If you read the scientific labeling with either food packets, or let's say the allowed level of pollutants in a particular environment, or in let's say water, you might also see other units such as ppm, which abbreviates as parts per million, where 1 million is 10 power -6. So parts per million is another way to represent this micro.
Okay.
Okay. So if I say the allowed number of pollutants of chlorine or sodium, let's say, in water is 36 parts per million, that means there is 36 micron parts of sodium in a certain amount of, or in water.
Okay.
Yeah. Any doubt in this?
No.
No. Okay, let's move on. So this is scientific notation. I know you used to representing data, or you've been asked to always represent data like this. The standard notation is, for example, if you have a value 500, write it as 5 into 10 power -2, 0.5, 5 into 10 power -1, 0.005, 5 into 10 power -2, so on and so forth. What if you have this data? What if you have 32.871?
So
What's the scientific way to represent this?
write it in the standard form, where
Okay.
before the decimal towards the left, there should be only one numeric value.
Correct.
Then
So you
you
would
have-
rewrite this as?
So 3.2871
Okay.
into 10 to the power 1.
You will shift it to the left. 1. Correct. Using scientific notation, you're representing this in its standard form. That is correct. How would you simplify this answer? Because you don't write 3.287, you approximate it, right? Using significant figures.
Yeah.
How do you decide that?
So you write it to the to 2 decimal places?
Is that always 2 decimal places? Or is there a standard rule that you follow?
I don't know about the standard rule, but I think we usually do it to 1 significant figure.
It depends on the data in the question. Let's say you received this data, this as the answer. When you process data or information given in the question, let's say the values were this. Let's say it was 1 kilogram, 0.5 second, and 48 meters. These were the data given. You process them and got some answer, 32.871. Okay, using them in some combination. So look at the significant figures of the data in the question. The first data is in 1 significant figure. The second 0.5 seconds, it's in
2 significant, 1 significant.
also 1 only, correct.
Yes.
The data 48 centimeter is in
2 significant figures.
So you decide to reduce this to the highest number of significant figures of the data represented. Of these 3 data represented, the highest significant figure is
2.
So you reduce your answer to 2 significant figure.
Okay.
What does the answer become when reduced to 2 significant figure?
3.3.
Good. The answer is greater than 0.25. So 3.3, if it's lesser than 0.25, you would have reduced it to 3. 3.2. 3.2 into 10 to the power 1. Understood?
Yes.
Yeah. SI units are the units, again, like we discussed a minute ago or 5 minutes ago. SI units are the standard units that you represent quantities in. For example, you said voltage is measured in volt, which is in fact its SI unit. When broken down, volt can be written as joule per charge, joule per coulomb. Or when you broke it down fully, you got kg meter square per ampere second cube.
Yeah.
Got it? So these are all the fundamental quantities we just discussed. The most common ones are length, mass, time. We also discussed the others. Any doubts in them?
No.
Remember to not confuse the symbol for a quantity with the symbol for its unit.
Yes.
Make sure to draw that distinction. Next, let's look at the most common instruments we use for measuring the common quantities, fundamental and derived, the ones you know of. So measuring length and time. Measuring length, you use a device known as a micrometer. I'll explain the whole premise and the working of this micrometer. A micrometer is usually used to measure, let's say, the diameter of let's say, a spherical ball, where the size of the spherical ball is much, much smaller, and you need to accurately measure it. It has 2 scales, as you see in the diagram. One is called the fixed scale, and the other is a scale on a revolving barrel. For example, let's say you are measuring a certain thickness or a certain diameter, and you notice this. You notice that in the fixed scale, the divisions are such that how many divisions do you see from 0 to 5?
10.
10 divisions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. So if there are 10 divisions, each division is worth how much?
0.5.
0.5. 0.5. Can you tell me the unit? It's right here.
0.5 millimeter.
0.5 millimeter. So you know that this reading is stuck. If you notice this reading exactly, it's stuck between which and which readings?
0.55.
0.55, or it's after 5?
Okay, sorry, 5.5
5.5 and
and 6.
good.
No,
That is right. Because you're right. Because it's 0. This is 1.
right.
This would be 2. This would be 3. This would be 4. And this would have been 5. So this reading is somewhere between 5.5 and 6.0. Am I correct?
Yes.
How much exactly is it between 5.5 and 6? Look at this.
I
So
think
here,
6
correct. The coinciding scale on the revolving barrel is 32 exactly. Do you notice?
is 32. No, 33.
I
Just,
think it's 32. Let
yes, it's
me
32. It's
clear
32.
out this. I
Just
think
I
it's
just zoomed it in. It's 32.
no problem. It's 32. Correct. So it is 32. So it's 32 divisions from 0 to 50. It's 32 divisions between 5.5 and 6. So what do you think the answer is? By the way, this scale goes from 0 to 50. Why 0 to 50? Because every division is 0.5 mm. This 0.5 mm, which is one division, corresponds to one complete rotation of the scale.
I didn't understand.
Exactly. Oh, wait, you said you didn't understand. Okay, fine. I said 0.5 mm corresponds to one rotation. That means when I rotate this scale once completely,
Mm-hmm.
when I rotate it clockwise or anti-clockwise, however it is intended to, I cover one division on the main scale or the fixed scale.
Okay.
That means there are 50 divisions here
Yes.
on this revolving scale, correct?
Mhm.
So 50 divisions on the revolving scale correspond to 0.5 mm.
Okay.
Think of it as unitary method. 50 divisions correspond to 0.5 mm.
Mm-hmm.
Right now, the divisions have stopped at 32. So your question is 32 divisions correspond to how many mm? If 50 corresponds to 0.5, 32 will correspond to, please use unitary method, cross multiply and tell me.
Okay.
50 divisions corresponds to 0.5 mm, 32 divisions should correspond to
0.32.
0.32.
Is that right?
Yes, that is correct. Yes, that is right.
Okay.
Sorry. So yeah, so 32 divisions correspond to 0.32 mm, which means the reading is exactly 0.32 mm after this reading on the main scale, which is 5.5. So I need to add this 0.32 mm to the main scale or the fixed scale, which is 5.5, giving me the combined reading as 5.82 mm.
Okay.
Got it?
Yes.
Yeah. So here I have assumed 50 divisions. There could be scales with 100 divisions. Please
Okay.
make sure to adjust your formula accordingly.
Okay.
Okay? Any doubt in this?
No.
No. Make
But
sense how
so
to read
these
data?
stuff like the usage of micrometer is asked in the examinations.
The usage of micrometer is not asked in the examination. This is mostly explored in your paper 6. You
Okay.
could be asked to perform an experiment where you will need to find, let's say, the surface area of a spherical ball.
So in our
Something
school,
easy.
we opted for alternative to practical, so we don't actually do practicals.
Correct. But in alternative practical, you need to explain briefly, right?
Yeah,
What
so
device to use,
so
which is a
this
micrometer,
will
and how to use this.
this might be questioned.
Correct. This might be question where knowledge will be important. Although you don't need to accurately teach how to get a reading. You might need to briefly in 2 or 3 sentences explain
Okay.
how to use this. Then it will help. But if you're doing practicals, yes, it'll be more advantageous because you'll be required to know the working. The vernier calipers works on a very similar premise. It has a fixed scale or a main scale and then a vernier scale.
Mm-hmm.
Here, you just look at the coinciding reading.
Yeah.
And then the coinciding reading will help you figure out the final value. The premise is the exact same. There is always a fixed scale or a main scale and then another scale where you see the first coinciding reading and then measure that.
Okay.
Okay. When it comes to measuring time, the simplest way of measuring time is by using a stop clock or a stopwatch. Although there is another way where you use a device known as a ticker tape. I'll explore more about the ticker tape next. Because if you do remember, you might have encountered a question or two, especially in your paper 4 or even paper 6, where ticker tapes are used
No,
to record time instants
not
during some type of motion.
not till now.
Not done, not done.
Hmm.
I'll teach you anyway, because in paper 4, you do get some questions.
Okay.
Let's look at volume and density. Volume is a fundamental and or a derived unit or a quantity, sorry.
Volume is a derived quantity.
What about density?
Density is also a derived quantity.
What's the formula that relates volume and density?
Density is mass upon volume. Sorry,
Density
mass.
is
Yeah, density is mass.
correct. Density is mass upon volume. So by logic, what is the unit of density?
Kg per meter cube.
Kg per meter cube is correct. Yes. Next, density is mass by volume. Its unit is kg per meter cube. Here's an example of a calculation done using the same formula. You can read through the example once and ask me if you have any doubts.
Okay.
Any doubts in this?
So the question is in the blue part, right?
Yeah, correct.
The data. Where's the table?
Using the data from the table above, calculate the mass of steel having a volume of.
But
So
I
here,
can't how to do
it's
it.
given
Yeah.
here. It's given here. So the entire table was used there. So I just copied the data, the density given here. Density is 2700. So if this is the density and and this is the mass, what is the volume? Anyway, any doubt how to use the formula?
No.
No. Again, remember, while solving numerical, make sure to write the units at every stage. So it's easier for you to figure out the unit at the end. Like I said, the advantage is you don't have to hassle.
Okay.
Next, when you measure volume, measuring volume, there are different methods you use. When you're measuring the volume of a liquid, the simplest way is to use volumetric flasks. Correct? Use volumetric flasks with observable graduations.
Mhm.
Make sure to pour them in the containers and then measure accordingly.
Okay.
Simple. When it is a regular solid,
Yeah.
one way to do it is regular solids always have formulas for volume. For example, if it's a rectangular block or a cuboid, its volume is length into breadth into height.
Mhm.
For a cylinder, it's pi r square h. For a cone, it is 1 by 3 pi r square h, and so on and so forth, right? So for a regular solid, you can either split it down into one of the basic shapes that we know of and then find the volume. Or if it is irregular, what's the simple way to find out the
So we
volume of an
use the
irregular solid?
displacement method.
Correct. This is also called the Archimedes principle, right?
Yes.
Yes, you
The
can use
principle
the Archimedes principle. Actually, Archimedes principle is an extension of the displacement method. It's slightly more complex and nuanced. But yes, the displacement method is one simple way for you to figure out.
If I'm not wrong, it's used when we solve questions about that ship that why does it still float despite the fact it's denser than the water.
Yeah, correct. Do you know why it does, by the way, since you asked the question?
Sorry?
Do you know why it does? Because
Yes,
by
because
logic,
uh,
wood floats but steel sinks in water. But a ship made of steel floats. Yeah,
yes, because the hollow space in the base in the base of the ship
the hull of the ship, correct?
it displaces so the ship displaces the amount of water as its weight.
Correct. Also, another way to remember it is the hollow space in the hollow space or the empty space which is occupied by air, which is so light, it is so light that it reduces the overall
weight of the ship.
density. Overall average density reduces, making it less denser than water. Okay. Yeah, that is right. So here's an example of the displacement method being used.
Okay. How do we define Archimedes' principle?
So Archimedes principle is a method. The simplest way to understand it is, think of it this way. If you have a container,
Yeah.
let's say that is filled up to the brim with a liquid,
Yeah.
and you have a solid of defined or that is regular or irregular shape, doesn't matter. When you submerge this solid completely within this liquid,
Yes.
when you submerge this, since the liquid was inside the container originally was filled up to the brim, there is a certain amount of liquid that will be displaced.
Mm-hmm.
So the displaced liquid or the amount of displaced liquid has a relationship with some property of the solid. Can you tell me what that is? Something will be same. Something of the solid will be equal to something of liquid displaced. What is that something?
The weight of the solid,
The weight of the solid,
or the force applied by the solid,
the volume,
the volume of the solid.
the volume.
Oh, okay. So can we define the principle as an object when immersed in water or submerged in a liquid displaces
Yeah,
the same amount of the liquid as its volume?
exactly. Displaces equal amount of liquid. By using this, you can find the density of the solid. You know its mass. You will figure out the volume from Archimedes principle. Mass and volume can help you figure out what density.
Yes.
Got it?
Yes.
Next. A relative density is also a quantity that you sometimes come across. It is the density of any substance when compared to density of water. That's
Okay.
hence the
Can I
word
just
relative.
make a note of it?
I'm sorry.
Can I just make a note of it? Just a
Yeah,
second.
please do. Please do. Sorry.
Relative density was density. Okay, sure. You can continue.
Any doubt in this?
No.
No.
When do we use relative density?
Relative density, in most cases, there is no physical application. It's a concept that is used to compare the density compare density of two objects.
Okay.
Numerically,
Like
I can
it
use
works
this
like
to
a
make your
percentage.
not percentage. It's a comparison. Percentage is a comparison to a total of 100 always.
Yeah, so this like
Density is a
the concept is similar, no?
The
Comparison.
concept is similar.
Yes.
Yes,
Okay.
yes. It is a comparison. I can use it to make your numerical more nuanced. From an exam point of view, that's what I can do. From a realistic point of view, relative density helps you compare the densities of two quantities. So a high relative density means that there is a vast difference between the density of object one compared to the standard object. A low relative density means that they are almost similar.
Okay.
So this is a way for me to understand information from numbers or take context from numbers.
Okay.
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 Next, I'll move on to the next concept, forces and motion. So what I'll do here is I'll first talk about motion. I'll split motion into different parts. Then I will talk about forces next. Once I've covered motion up until acceleration and the motion graphs. Okay.
Okay.
So we'll look at all these concepts once, and then I'll help you write them on the board. Fine.
Yeah.
Okay. Again, for context, I'll talk about uniform motion, non-uniform motion,
Okay.
the different ways you can represent uniform, non-uniform motion, or the different formulae involved for all quantities: speed, velocity, average speed, average velocity, distance, displacement, acceleration, everything. Then we look at how information is relayed on a graph, what you can understand from the shape of the graph, what you can understand from the slope of the graph, what you can understand from the area under the graph, or what quantity represents each of these concepts or each of these things that I give. And then we will look at forces. I will dissect forces using Newton's laws, and then we will explore further into forces, moments, all of these. Okay. So let me start with motion. So what I'll do is I'll discuss the different types of motion, and then I'll go ahead and show you the slides. Let's start with uniform and non-uniform motion. Can you define in simple words what are uniform and non-uniform motion?
When an object is motion when an object is maybe when talking about speed, if an object is traveling equal distances in per unit time or in equal intervals of time, it's said to be moving uniformly.
Okay, correct. Then what is non-uniform motion?
When an object is covering unequal distances but in those per unit time or in equal intervals of time, then it's said to be traveling non-uniform.
Equal or unequal, doesn't matter.
Okay.
Correct. Basically, if a body is able to cover equal distances in equal intervals of time, it's uniform.
Mhm.
If it doesn't, then it is non-uniform. That's it. Let me give you an example. Let's say a body covers 100 meters in the first 10 seconds,
Yes.
and then again another 100 meters
Mhm.
in the next 10 seconds. Is this uniform motion?
Yes.
What if it covers 200 meters in the next 20 seconds? Is it still uniform?
Yes.
It is still uniform, correct. 500 meters in the next 50 seconds?
Yes.
Yeah, that's it. Or in other words, if you notice, the distance covered per unit time is the same in all these three cases. The distance covered per unit time is still 10 meter per second, 10 meter per second, 10 meter per second, correct? This distance covered per unit time is given a name. It's called, what is it called? What is
Sorry?
distance covered per unit time called?
Speed.
Speed. So the formula is speed is equal to distance by time, correct?
Yes.
Yeah. If the speed is unequal in even one of the intervals given, then the motion is considered to be non-uniform, correct?
Yep.
Here, does speed still have the formula distance by time? Distance by time?
Hmm.
It does, but only in those instants or intervals. For example,
Yes.
in the first interval, it covers 100 meters, let's say in 8 seconds. And then it covers 200 meters in, let's say,
10 seconds.
25 seconds. Okay. Any amount of time.
Yeah.
First interval, what is the speed?
100 by 8 is 12.5.
Okay. In the second interval, what is the speed?
8 meter per second.
So the speed is different in each interval, giving you the sense of non-uniform motion. Clear?
Yes.
So let's look at speed to begin with. So speed is correct, defined as distance per unit time. What is average speed? Because I seem to have written the formula for average speed here.
Average speed
Average speed, how is it different
total.
from speed?
Okay, so if an object is moving and takes rests in between, so while calculating the average speed, the formula is slightly different. It says total distance traveled upon total time taken.
Hmm.
So we'll include the distance traveled and even the time taken for the rest.
Correct. If I go back to my previous example, look here. Look at this example.
Yes.
So in here, can you calculate the total distance traveled in this case?
400 meters.
Correct, 400 meters. What is the total time taken?
10, 10, 20, 40 seconds.
Correct. So what is the average speed in this case? Total distance, which is 400 divided by time, which is 40
10
seconds.
seconds.
10 meter per second. Do you notice how it's the same as the instantaneous values of speed in each interval? 10, 10, 10. Look at this one. In this case, what is the total distance traveled?
300 meters.
Divided by, what is the total time taken?
33 seconds.
Here, what do you get the total, the average speed to be?
300 by 33. Which will be 9.1 something. 9.
Correct. 9.09 or 9.1
Yes.
meter per second. You'll notice here that the average speed is not equal to any of the instantaneous values.
Yes.
So this is also another way you can differentiate between uniform and non-uniform. If the average speed is same as instantaneous values of speed in each interval, then the motion is uniform. If the average speed is different or speed in each interval is also different, then it is non-uniform motion. Got it?
Yes.
Any doubt?
No.
No. Okay. So this is speed. Next, let's look at velocity. To look at velocity, I also need to look at displacement and distance first. So this brings me to the concept of scalars and vectors, which I did not discuss till now. I'll start discussing scalars and vectors first, then we'll look at distance and displacement, which are examples of scalars and vectors. Let's start with scalars and vectors. What is a scalar? What is a vector?
So
What
there
is
are
the
types of
difference?
quantities. A scalar quantity can be defined completely only by the magnitude or the amount, and a vector quantity requires the direction also. So an example of scalar quantity can be mass, which can be measured using scale balance.
Correct. Weighing balance you can use. And mass does not have direction, you say?
No.
No. Okay.
And
And then?
the corresponding vector quantity for it can be weight, which is derived from the formula mass into gravity.
Correct. It's a type of force.
Yes,
Correct.
and it is
Force is also a
applied
vector.
in the downwards direction. So
correct. Weight is not, for example, if a body is of mass 10 kg, if you assume acceleration due to gravity also is 10, then its weight is 100 Newton. Correct?
yes.
M into G. But this weight is always acting in one direction. Usually, if you take the Earth into context, weight is always acting downwards for a body, towards Earth. Correct?
Yes.
Okay, fine. So in this case, you're telling that weight is a vector because it cares about direction. Mass is a scalar because it does not care about direction. Correct? The same also applies for distance and displacement.
Yes.
Can you tell me what is the difference between distance and displacement?
So distance is the length traveled by an object, the length of the path traveled by an object, and displacement is that path with the direction in which an object is traveling. And for displacement, it's necessary that the starting point and the ending point are different.
Not necessarily. For displacement to be non-zero, they have to be different.
But if displacement is zero, then what's the point of displacement?
It is. Correct. It will be zero if the starting and the final points are the same. That is correct. Okay. So I'll show you a few examples here. Look at these paths. I've highlighted 4 paths in 4 different colors.
Yes.
Which ones of these are distances and which one of these is the displacement?
All of these can be distances.
Good. Correct. That was a trick question. All of these can be distances, but only one of these can be displacement, which is
A to B.
correct. Pink can be displacement, but it's just that the displacement S will be equal to 0 in this case. This is displacement. Got it? It is the shortest distance between 2 points, which is always a straight line. Correct. Next. So velocity is basically speed with direction, correct? Because its formula is velocity V equals displacement S by time t. So to denote the fact that velocity is a vector, I'll keep writing an arrow mark on top. Okay. Fine.
Yeah.
Okay. Next, what is acceleration, and is it a scalar or a vector?
Acceleration is a vector quantity. It
Okay.
is basically the rate of change in velocity.
So, for example, if a body, let's say, is traveling from one point to another, let's say it had an initial velocity of u, and let's say by the time it reached the destination, it had a final velocity v, and the
So,
displacement. Correct.
please complete.
So, and the displacement that occurs here is s in time interval t. Then your equation for acceleration is change in velocity by time,
Yes.
which is v minus u by t. Correct?
Yep.
Yeah. Any doubt in this?
No.
No. In fact, this formula rewritten gives you the first equation of motion. Correct?
Yes.
Yeah. If you rewrite it in terms of v, what do you get? V is equal to?
V is equal to AT plus U.
Correct.
U plus AT.
Correct. That's it. Doesn't matter how you do it.
Yeah.
This is the first equation of motion. Any doubt in this?
There were 5 equations of motion, no?
There are, yes.
Right.
Any doubt? Anything you want to explain again?
No.
No. Okay. So here's an example being solved. You can have a look at the example, how it is solved,
The
and then you can
coordinate
let
of
me know.
body passes first change the velocity. Study acceleration, velocity 5 seconds later at B. R is gaining every second. 15 plus, okay. Right. Got it.
Okay, fine. Next, before we go to motion graphs, I'll give you the other two equations of motion as well. The other three, I think. So let's start with the first equation that we wrote. The first equation was V equals U plus AT, correct? Next, what is the second equation of motion? That's written in terms of displacement S. S equals?
S is equal to half, sorry, wait.
UT?
Half AT square plus UT?
Correct.
Yes.
UT plus half AT square. What about the last one? V square equals?
V square equals 2AS? No.
U square plus 2AS.
2AS, yes.
You can also write displacement S if the acceleration is uniform. S is equal to U plus V divided by 2 times T. You can use this also.
This is derived from which one?
This is written using the formula total displacement equals average velocity into total time.
Average velocity.
The average velocity formula. Average velocity was total displacement by total time. Now, when you rewrite it, you get total displacement equals average velocity into time.
Okay.
This equation is conditional. It is going to assume that the motion is in only one direction and acceleration is going to remain uniform. That's what it assumes.
Okay.
Okay. Any doubt in this?
No.
No. There is one more equation, displacement in the nth second.
Sorry?
There is one more equation for displacement in the nth second. Do you know what that is?
No.
Can you derive it for me? Displacement in the nth second. For example, let's say the motion occurs for 10 seconds. If I ask you what is the displacement that is occurring in the 6th second, how do you find that out?
So will it be
At the 6th second.
okay? So is it going to be SM? No idea.
It's U plus
Yes.
1 by 2 A into 2n minus 1. Do you know how this works?
No.
Simple. Displacement in the nth second is whatever displacement happened up to n seconds minus whatever displacement happened up to n minus 1 seconds. That's it. Simple.
Okay.
For example, if I ask you whatever displacement happens in the 6th second, It is nothing but total displacement up to 6 seconds minus total displacement up to 5 seconds. That's it.
Oh, okay.
That's how I got. I just substituted t as n and then t as n minus 1 in this equation, and then subtracted both to get the displacement in the nth second. That's it. Clear? You can do this to confirm if you want. So when you said 5 equations, no, so I decided to give you all 5. 1, 2, 3, 4, and 5.
Okay.
Fine.
Yes.
And all these equations apply specifically for non-uniform motion, because all of these are going to assume a non-zero constant acceleration. Clear?
Yes.
Any doubt in this?
No.
No. You can take a minute to note them down. I'm happy to move on after you're done noting them down.
Okay. Done.
Done? Okay. Next. So when you go to motion time graphs, I'll explain you the general rule of thumb that we follow. So you have to first understand the information about the shape of the graph and how you understand what you understand. If the two quantities y and x have a linear proportional relationship, what will be the shape of the graph?
Straight line inclined to the x-axis.
You mean to say a straight line with a constant positive slope, right?
Yes.
Yeah. What if it's y proportional to negative x?
A straight line with a constant negative slope.
Good. What if it is y proportional to x square?
A steeper straight line.
A line with an increasing slope or an exponential graph. What
Okay.
about y proportional to 1 by x?
Like the graph we draw for deceleration.
Correct. How will it look for y proportional to 1 by x square in that case? It will be the same shape as y proportional to 1 by x. It will just be
It's
more
going to be
steeper.
okay.
It's just going to be a little bit more steeper. That's it. Yeah?
Isn't the shape different?
No. You can plot it on Desmos once and check if you want.
Oh, okay, this one. Okay, fine. Yeah. I
Yeah.
confused it with the previous one.
Okay, fine. Next. What about x proportional to y square? I'll tell you why I need this.
X proportional to y square. Okay. Should I try drawing it?
Yeah, you tell me. What will the shape look like?
Okay, just a second. Is it going to be like just a second? Is it going to be like this only?
No.
No?
That is y proportional to 1 by x. No?
Oh, right.
X proportional to y square.
Then maybe just a
Or
second.
rewritten as y is equal to y proportional to root x. Want to write it that way also, you can write. You can plot it on Desmos. I'll give you a minute. Open Desmos. Write x equal to y square.
Open
And
what? Sorry?
the shape. Open Desmos or any graphing calculator app or website. Type the equation x equal to y square. Tell me what shape it looks like.
X equals y square. Oh, okay. It's a U kind of thing.
Yeah,
It's like this.
exactly.
I think it's going
Yes.
to be on the axis like that.
Exactly. Yes, it's going to be on the axis. So I'll make sure to draw it like this. I'll make sure to draw it like this. I'll tell you why I need this. Okay. Now, all you need to remember is there are different type of graphs. There is a displacement time graph. There is a speed time or a velocity time graph. There is an acceleration time graph.
Yes.
You need to know what the slope and the area represent in each case. Let's start one by one.
Can I just note all of these down? Just a second.
Yeah, please do it. As I write, please note.
I wish we were taught like this in school.
See, the point is teachers sometimes forget that physics and math, they do cross-link.
It's not that, it's just that it's not so like logical and interactive. Believe me or not, we've never done the fundamentals, like breaking down the equations in school.
Is it? It's okay. I'm glad they didn't do it that well. Otherwise, I would be out of a job.
Right. Done.
Okay.
Yep.
So displacement time graph can also be interpreted as distance versus time, assuming direction doesn't change.
Yes.
And velocity versus time can be interpreted as speed versus time, provided direction does not change. Okay. Yeah. Now, what is meant by slope? Can you tell me that?
The gradient of the graph, or the
Or can I
ratio
say it is the
between
change in y quantity by change in x quantity?
Yes.
Then area is just change in y quantity into change in x quantity.
Okay.
Multiplication instead of division. Is that correct?
Yes.
Yes, that is right. Okay. So in a displacement time graph, what does the slope represent? Please tell me that.
Speed.
The slope represents speed or velocity. Correct.
Yeah.
Good. Because it's change in displacement by change in time, which is nothing but velocity. We just discussed a slide ago. What does the area represent? Displacement into time. Is there any such quantity? Displacement into time?
No.
There isn't. So area represents nothing.
Yes.
Now, velocity time graph, what does the slope represent? Change in velocity by change in
Acceleration.
time. Exactly. What does the area represent? Change in velocity into change
The
in time.
distance.
Distance or displacement. Yes. Or total displacement, if it's the total area. In an acceleration time graph, what does the slope represent? Is there any quantity that we've discussed?
I
It's
don't
called acceleration by time?
know.
No. So it represents nothing, can I say?
Yes.
Then what does the area represent? Change in acceleration into change in time.
I don't think so. Anything.
You sure? Go back to one of the formulas. A
Change.
equals V minus U by T. If
Change
you
in
cross multiply, what do you get? Correct. You said something.
velocity.
Change in
Change in
velocity. What you
velocity.
said
This is
initially was
acceleration again. Change. Oh, that's
no.
rate. Change in velocity. Okay. Change in velocity.
Correct. Correct.
Yeah.
So this represents the change in velocity. Students always mistake. They assume it is velocity because many a time graph will start from the origin, which means initial velocity is zero. But on the odd occasion that it doesn't, you have to remember it's not velocity. The area is not velocity. Area is change in velocity,
Yeah.
or it is V minus U.
Okay.
Got it?
Yes.
V minus U. This is what the area represents.
Okay.
Any doubt in this?
No.
Now, you don't have to by heart all the different possible shapes. You have to know how the graph looks for y proportional to x, minus x, x square, 1 by x square, x proportional to y square, all of this. Okay. So now let's start. For a body at rest, I'll ask you, how does the displacement versus time graph look? You tell me one of these shapes, y proportional to x, y proportional to minus x, whichever one you think. For a
For a
body
body
at
at
rest,
rest, none.
I
None
think
of
I
these.
forgot to write one more shape, which
Yeah.
is relevant to you. That
Yeah.
shape is, there are two more actually.
A
One is y
horizontal
equal to
line.
0, which
Yes.
means there is nothing on the graph, or correct, y being a constant,
Hmm.
which means the graph will be a straight line parallel to x-axis. So now tell me, in a displacement versus time graph, when a body is at rest, how does the graph look?
Y equals 0.
If a body is traveling with constant velocity,
Y is proportional to x.
if a body is traveling with increasing velocity or constant acceleration,
Y is proportional to x square.
how? Prove to me. Your
Because
answer is right. Prove it to me.
It's because it's traveling with increasing velocity, but we don't know whether it's traveling with uniform velocity or not.
No, think of
So-
it this way. Acceleration is change in velocity by time, correct?
Mhm.
Velocity is change in displacement by time, correct?
Yes.
Which means I can rewrite this formula as S by,
T squared.
this is of the form.
Oh, okay.
Simple.
Yes.
So if acceleration is positive, it will be y proportional to x square.
Yes.
If acceleration is negative, how will the displacement versus time graph look?
If
Think and
acceleration
tell.
is negative.
Negative. That means negative means the body will eventually come to rest, which means its displacement should eventually become constant.
Eventually, y is proportional to 1 by x.
But that would mean that displacement is negative or decreasing. That's not the case, right?
Okay, right.
Think
Okay,
of it this way.
so
If a
is-
car is slowing down, it's still moving, correct? It's not
Yeah.
moving the opposite direction.
Yes.
But it will eventually come to rest. What the logic is correct. What you're thinking is right. The displacement time graph should eventually become a constant.
Yeah, will it be like, just a second?
It's one of the shapes that we've drawn.
It's one of the shapes. It will not be something like this. No.
It's x proportional to y square, isn't it?
X.
Because displacement, notice, eventually displacement is becoming a constant value,
Yes. Okay.
isn't it?
Yes.
Yeah. That's why I wrote that shape. That shape is applicable to the situation. A
Okay.
displacement time graph when acceleration is negative. Got it?
Yes.
This is basically an exponential equation with a decreasing slope. This is an exponential equation with an increasing slope.
Okay.
Got it?
Yes.
Yeah. Next, how will the velocity time graph look for a body at rest?
How will it will look like y is a constant.
For a body at rest, it will be y equal to 0. For a displacement time graph, it would be y equal to constant. Got it?
No, wait. For a body at rest,
the displacement is the same. For example, if it is like 5 meters away, let's say there's an object 5 meters away from. If it is at rest, it will continue to stay at that 5 meters, correct?
yes.
So the displacement time graph for a body at rest would be of the shape y equals
Right.
a.
Yeah. Okay.
The velocity versus time graph would be 0 because it has no velocity because it is at rest.
Yeah.
Yeah. How would the velocity versus time graph look for a body moving with constant velocity?
Y equals a.
Very good answer. Increasing velocity or uniform acceleration?
Y is proportional to x.
Uniform deceleration or negative acceleration? The
Y
slope
is
should be
proportional
negative.
to minus x.
Correct. Now, okay. Increasing acceleration?
Y is proportional to x square.
Correct. Decreasing acceleration?
Y is proportional to 1 by x.
1 by x square.
1 by x. What's the difference?
Correct. 1 by x square because the time will be squared in this case.
Oh, okay.
Time would be to the power 1. Time will be to the power 2. That's why. Next. Okay, I think you know that this. How will the acceleration versus time graph look for a body at rest?
Y equals 0.
Constant velocity?
Constant velocity. Y is proportional to x.
No. Constant velocity. How will the acceleration versus time graph look? If a velocity is constant, what does it say about the body's acceleration?
The acceleration is constant.
Or 0? Acceleration is
Yeah,
change in
0.
velocity by time.
So
If
it
there
will
is
be
no,
y equals a.
it'll be y equals 0 only again. Because acceleration is still 0, no? Whether the body is at rest or traveling with constant velocity.
Okay.
Acceleration will still be 0 in either case, won't it?
Got it.
That is why if you notice, we assume translational equilibrium as that point or as that instance where the body is either at rest or traveling with constant velocity. Because in both the cases, acceleration will be clear.
Okay.
Yeah.
Yeah.
Next, how will the acceleration versus time graph look for the body with constant acceleration?
Y equals x. Sorry, y is proportional to x.
Y is equal to a. Because
Oh,
constant acceleration.
Yeah, right. Sorry, go. I
Correct.
messed up again.
Constant deceleration will still be y equal to a, but technically it will be y equal to negative a. or the line will be below the x-axis. Just remember that. Okay.
Yes.
This is y equal to a. This is y equal to negative a. Just remember that. This will be the graph for constant deceleration. Increasing acceleration is this, y proportional to x.
Okay.
Deceleration, decreasing deceleration is this, negative x. That's it.
Okay.
Clear? Although we don't explore those two anymore at all because it doesn't help, right? Increasing acceleration, decreasing acceleration, there's nothing you can interpret from that.
Okay.
Any doubt in this?
No.
So this is how you understand mathematically the implication of the shapes of the graph on the slope, the area, and the type of motion it is executed. Make sense?
Yes.
Yes. Ask me if you have any doubts. I'll keep the diagrams on the board for a minute.
Not here.
No doubt?
No.
Okay. So now I'll just show you the slides which are going to interpret what I taught. So this is a car traveling with a steady speed. You notice its distance or displacement versus time graph is aligned with a constant slope or y proportional to x. You see it?
Yes.
Okay. Next. This is a car accelerating. So it's of the shape y proportional to x square. This is a car that is stopped. So it's distance versus time graph. Do you notice? It's not y equal to 0. It's y equal to constant.
Yes.
Because it will stay at that particular constant displacement throughout. But if it is at the origin, then it will be y equal to 0. That's it.
Okay.
So this is how you interpret speed time graph. Again, you can see the shape. Body is traveling at steady speed, steady acceleration. And then you can interpret the same for acceleration versus time graphs as well. Now, this is the ticker tape I was talking to you about. You will come across paper for past year questions at least with this ticker tape. I'll show you what ticker tape is. Okay. Actually, can you read through this and can you teach me what ticker tape is?
Okay. In the laboratory, motion can be investigated
You
using
can read
trolley.
in your mind. You don't have to
Okay.
read loud. That's okay.
Okay, so basically, it's kind of a device. Like for speed, we use light gates. To calculate time, we'll use
Yeah.
the ticker tape.
It's very similar to light gates. I was about to say that.
Yes. So the basic logic is that there's this machine which punches holes in the tape, and like it says, the typical timer produces 50 dots per second, and we can determine how fast or how slow the object is traveling by the number of dots produced or the distance between the dots. Obviously, if
Correct.
it's traveling fast, the distance is going to be more, and if it's traveling slowly, the distance is going to be less.
How do you interpret that? How does that make sense that the distance is going to be greater for a higher speed?
It says that a typical timer produces 50 dots per second if it's traveling faster. So those 50 dots will be produced. The tape will be
Much
able
farther.
to go further distance before the
Uh,
dots were punched.
Correct. Exactly. So ticker tape is basically a simple way for you to guess whether the motion is uniform or non-uniform. Simple rule of thumb, if the distance between the dots, whether it is big or small, doesn't matter. If the distance continues to stay the same, then the motion is what? Uniform or non-uniform?
Uniform.
But if the distance begins to change,
Then it's
then
not.
the motion non-uniform. The first two are examples of uniform motion, you can see. Because in both the cases, the distance is the same. The
Yes.
last two are examples of non-uniform motion. Can you see?
Yeah.
So for constant acceleration, the distance keeps on increasing, which means it covers more and more and more distance with each interval as time progresses, which is correct, no? Because as a body is accelerating, it will cover more and more distance with each interval of time, correct?
Yes.
But by an accelerating body, let's say in the first second, it might cover only 5 meters. But in the last second, just before it stops or motion is recorded, it could cover like 10, 15 meters because the velocity has increased.
Understood.
Here in the fourth one, you see an example of acceleration and then retardation as well. Do you see?
Yeah.
And when the distance between the dots practically becomes 0, that means the body is in a state of
Rest.
good. Yes. Any doubt in this?
No.
This is it. This is a ticker tape is again a tool for you to measure, understand, interpret motion. Got it?
Yes.
Okay. Calculations from tape, just measure the intervals. That's it. If there are 50 dots, then every 5 dots is going to give you 0.1 of a second. Okay.
Yes.
We will mention the divisions. Don't worry about that. Let's look at free fall. This is a special type of motion. What is free fall? And before you explain, I wanted to explain whether it is uniform or non-uniform motion.
I think it is non-uniform.
You are correct. It is non-uniform because the body is subjected to,
The force of gravity.
yes, gravitational force or weight or force of gravity, like you said. So for is it uniform or non-uniform? You said non-uniform, right?
It's non-uniform.
Correct. So to begin with, let's say the three equations of motion, S is equal to ut plus half at square, v equals u plus at,
Yes.
and the one combined from these two, v square equals u square plus 2as. How does this change? Two conditions. When a body is falling down or when a body is thrown up.
Okay.
When it is falling down, what changes do you make to the equation? I'll start. Instead of displacement S, you say height h. What else?
And
Acceleration A will be replaced by
deceleration.
plus G. Acceleration due to gravity G,
Okay,
which
plus
is 9.81 meter per second square. Correct? Remember?
yes.
Every body falling towards Earth will fall with a constant acceleration of 9.81 meter per second square. Remember? Yeah. So in other words, acceleration is going to be positive. Is that correct?
Yes.
Yeah. And when the body reaches the ground or just before it reaches the ground, it's going to reach maximum velocity.
So
And when it starts, initially, when a body is thrown from the height, that when it is thrown from maximum height, you usually assume initial velocity u to be 0.
yeah.
It's thrown from maximum height. Because allowing a body to fall down is just letting it fall down like this. Notice? You don't give any velocity. So initial velocity is always 0 when it is thrown from maximum height. Clear?
Okay.
What about the opposite? When it is thrown up, how do the equations change?
I think S still changes to H.
Correct. Acceleration here will be?
Minus 9.8.
Exactly. Minus 9.81 meter per second square. It's going to be deceleration.
And U
at
still going to
max,
be the same.
correct. And then when it reaches maximum height,
Then
instead of initial velocity, what will become 0?
final velocity.
Good, final velocity. Because when a body is decelerating, it should eventually come to a state of rest, correct? It does, in fact, when it reaches maximum height, for a fraction of a second, it stays at rest. And at that point, final velocity v becomes 0.
Okay.
Understood the changes to make in the equations of motion?
Okay.
Any doubt in this?
No.
In this, and this. Any doubt?
No.
No. Okay. Anything you want me to explain again? Didn't understand?
No.
No. Move on?
Yes.
Okay. Here's an example. Remember, ideally speaking, there is no loss of energy, assuming there is no air resistance. So whenever a body goes up and comes down, it retains the same values. If it is thrown up at 30 meter per second, it will ideally fall back at the same speed, at the same height, which is 30 meter per second.
Okay.
This assumption is made based on the fact that there is no energy loss. Practically, is that true though?
No.
There is always energy loss, which means the body might not always come back or return with the same velocity with which it was thrown. Clear?
Yeah.
Any doubt?
No.
Here are motion time graphs for a body with steady acceleration, zero acceleration, and deceleration as well. Any doubt in the shapes?
No.
No. Next, let's talk about force. I'll give you the introduction to force, and I'll talk about Newton's laws and some common forces. We will explore more of forces, energy in the next class. Okay. Let's start with force. Can you define what a force is to me?
A push or a pull?
A push or a pull? I agree. Okay, fine. Uh, fine. What effect does force have on a body? Let's understand. See, sometimes you can define a quantity through its formula itself. Correct? Like
Yeah.
speed is distance over time or rate of distance covered. But
Hmm.
sometimes, like a quantity like force or mass, for example, you
Yeah.
define it by the effect that it has.
Yes.
What all effect can force have on a body? I'll give you this.
Can-
I'll start. I'll tell the simpler answer.
Okay.
Force can move a body.
Yes. It can stop a body.
Correct. It can stop a body. What else can it do?
It can change the direction of the body.
Change direction of a body.
Mhm.
What else?
It can change the
Can it
speed. of the
change
body.
speed is still in motion only.
Okay.
What about changing shape? Can it do
Shape. Yeah. I was going to do that. Change the
that?
shape.
Okay. What else? What else can force do?
It can rotate the body. Nice.
Provided the body is fixed about an axis.
Yes.
Correct?
Yes.
Force can also help keep a body in circular motion. We'll learn that in centripetal force once we go to the
Okay.
next class. Okay.
Yes.
So forces can do all these things for a body. It can move a body, it can stop a body, it can change its direction, change the shape, rotate the body about a given axis. Force can do all of these things on a body.
Mhm.
This is how you understand the effect that force can have on a body. Clear?
Okay. Yeah.
What is the formula for force? F equals.
Mass into acceleration.
This is derived from Newton's second law. How did I derive it? In the simplest possible way. Let's say I'm living in a world there where there is no concept of force. I'm the first one to invent it. I'll say force acting on a body is proportional to two things: mass and acceleration. How do you convert a proportionality into an equality?
By using a constant.
Correct. I'll write F is equal to K into MA. But since I'm inventing the quantity force, I can invent a value for K as well. I'll take the value of K as 1, giving me my final equation. F is equal to M into A.
Okay.
Its SI unit is kg meter per second square or Newton. Both work. Clear?
Yes.
Any doubt in this? Anything you want me to explain again? Didn't understand?
No.
No. Okay. I'll keep this on board. Just go through. Ask me if you have any doubts about force.
It has direction as well. Got it.
It changes direction as well. Yes, correct. Yeah. So next class, I will talk about Newton's laws. We'll interpret all the different types of motion or every behavioral changes we notice as a consequence of Newton's laws, and how we interpret Newton's laws in our day-to-day examples, whether it is moment, whether it is momentum, whether it is action-reaction pair, all of these, also collisions. And after that, I will look at the energy part, which will cover the first unit. Okay.